Welcome to this lecture on group theory. Today, we are going to explore a fascinating mathematical structure known as the group of units modulo n. If you have ever wondered how digital security works or how numbers can loop around like a clock to create perfect, predictable patterns, you are in the right place. We will build this concept from the ground up, starting with simple analogies and working our way to formal proofs. By the end of this video, you will completely understand what this group is, how to find its elements, and why it is the invisible shield protecting the modern internet. Let us dive in. Now that we know our topic, let us start with a simple analogy. Imagine a special clock with n hours on it. But this clock represents a strict exclusive club. The bouncer at the door is the number n. To get into this club, a number must be positive and smaller than n. But there is a stricter rule. The number must share absolutely no common building blocks or prime factors with the bouncer n. In mathematics, when two numbers share no common positive divisors other than the number 1, we call them relatively prime or co-prime. If a number passes this test, it gets in. Inside this club, the only activity allowed is multiplication. But because it is a clock, whenever a multiplication result exceeds n, we wrap around by dividing by n and keeping only the remainder. This is what we mean by modulo arithmetic. Building on our club analogy, the numbers that survive this strict filtering process form a special mathematical family called the group of units modulo n. The mathematical operation that glues this group together is multiplication modulo n. For this set to be a valid group in abstract algebra, it must satisfy 4 strict rules: closure, associativity, having an identity element, and having inverses. The identity element is simply the number 1. But the most magical part of this group is the guarantee of inverses. Every single element inside it is guaranteed to have a multiplicative inverse. This means you can always multiply any element by another specific number in the set, and the result will wrap around the clock to get you exactly back to the identity element, which is 1. Now that we understand the rules conceptually, let us look at how mathematicians write this formally. This formula defines our group using set builder notation. The capital U of n represents the group of units modulo n. Inside the curly braces, we see x in Z, which means our elements x must belong to the set of all integers. The vertical bar means such that. Next, we have the size limit. X must be greater than or equal to 1 and strictly less than our modulo base n. Finally, we have the mathematical bouncer. GCD of x and n equals 1. This means the greatest common divisor of our element and the base must be exactly 1, ensuring they are relatively prime. If a number x satisfies all these conditions, it belongs to the group. Before we prove why inverses always exist, let us see this formula in action with a concrete example. We want to find the elements of U of 8 and prove it forms a valid group by finding the inverse for every single element. First, we list all the positive integers less than 8. These are our candidates, 1 through 7. Next, we act like the bouncer. We need to kick out any number that shares a common factor with 8. Since 8 is an even number, its only prime building block is 2. Therefore, we must remove all other even numbers from our list, which are 2, 4, and 6. The numbers that survive this filtering process are 1, 3, 5, and 7. This is our official set of elements for U of 8. This brings us to the next step, finding the inverses. To prove U of 8 is a group, every number must multiply with something to give a remainder of 1. The number 1 is the identity element, so multiplying 1 by 1 always gives 1, making it its own inverse. Next, let us test the number 3 by multiplying it by itself. The normal multiplication of 3 and 3 gives us 9. However, we are operating modulo 8, which means we must divide this result by 8 and keep only the remainder. The number 8 goes into 9 exactly one time, leaving a remainder of 1. Because the remainder is 1, we have found our inverse. The number 3 is its own inverse in this group. Continuing with our set, let us perform the exact same test for the number 5. Multiplying 5 by itself gives us 25 in standard arithmetic. We divide 25 by 8, which fits 3 whole times to make 24, leaving a remainder of 1. So 5 is also its own inverse. Finally, if you test 7, you will find that 7 times 7 is 49. Dividing 49 by 8 gives 48 with a remainder of 1. This is a fascinating property of U of 8. Every single element is its own inverse. Physically, this means applying any operation twice returns the system perfectly to its starting state. We have successfully verified the group. Now that we have seen one example, let us look at a second one, where elements are not always their own inverses. Let us find the elements of U of 10. We start by identifying the prime building blocks of the number 10, which are 2 and 5. This means any number that is even or any number that ends in 5 must be excluded from our set. We list the numbers from 1 to 9, and after applying our filter, we are left with exactly 4 elements: 1, 3, 7, and 9. These are the numbers that are relatively prime to 10. Now we need to pair them up based on their multiplication results to find their inverses. With our set established, let us find the inverses for U of 10. The number 1 is the identity, so its inverse is just 1. Now, let us try to find the inverse of 3. We need a number that multiplies with 3 to give a remainder of 1 when divided by 10. We test multiplying 3 and 7 together, which gives 21. When we divide 21 by 10, it goes in twice to make 20, leaving a remainder of exactly 1. This proves that 3 and 7 are inverses of each other. Finally, let us check the last remaining number, which is 9. When we multiply 9 by itself, we get 81. Dividing 81 by 10 leaves a remainder of 1. Therefore, 9 is its own inverse. We have found an inverse for every element. To visualize what we just calculated, we can look at this Cayley table for U of 10. A Cayley table is simply a multiplication grid for a group. Along the top and the left side, you see our group elements: 1, 3, 7, and 9. Inside the grid are the results of multiplying those elements modulo 10. Notice the highlighted cells containing the number 1. Every single row and every single column contains exactly one instance of the identity element. This perfect symmetry visually proves that every element has exactly one unique inverse. You can clearly see how 3 and 7 intersect at 1 and how 9 intersects with itself at 1. This grid captures the entire structure of the group. So, we have seen through examples that inverses always exist. This brings us to the formal proof. How do we know for sure that every element in any U of n has a multiplicative inverse? To prove this, we rely on a famous mathematical rule called Bezout's identity. We start with an element A in our group. By the rules of the group, A and the modulo base n share no common factors, meaning their greatest common divisor is 1. Bezout's identity states that if two numbers have a greatest common divisor of 1, you can always find two integers, let us call them x and y, to satisfy the linear equation. A times x plus n times y equals 1. This equation is the key to finding our inverse. Now that we have Bezout's identity, let us manipulate it. We can rearrange the equation by moving the n times y term to the right side. This gives us a times x equals 1 minus n times y. This shows that the product of a and x is exactly 1 unit away from a multiple of n. In the world of modulo n arithmetic, any multiple of n is treated as 0. Therefore, when we apply modulo n to this entire equation, the n times y term completely vanishes. This leaves us with our final result. A times x is congruent to 1 modulo n. This tells us that x is the exact number we need to multiply by e to get a remainder of 1. Therefore, x is the guaranteed inverse of a. So, we have proven that inverses hold. This brings us to a very important question. Why do we care about the group of units modulo n? It turns out that this specific mathematical structure is the absolute foundation of modern digital security. Every time you send a secure message, buy something online, or log into a website, an algorithm called RSA encryption protects your private data. RSA encryption relies entirely on the properties of U of n, specifically when n is the product of two massive prime numbers. The size of this group acts as the secret mathematical key that locks and unlocks your information. Without the predictable, structured behavior of inverses that we just proved, secure internet communication would be mathematically impossible. Let us summarize the key takeaways from this topic. First, the group of units modulo n consists of all positive integers smaller than n that share no common prime factors with n. Second, this set forms a robust mathematical group under multiplication modulo n, satisfying all group axioms. Third, thanks to Baseout's identity, every single element is guaranteed to have a partner that multiplies with it to yield a remainder of 1. Finally, this beautiful and simple structure of remainders and co-prime numbers is not just abstract math, it forms the invisible shield protecting all modern digital communications. You have now mastered the fundamentals of the group of units modulo n.